Hi, I'm Zor. Welcome to Unizor Education. We continue talking about variations, the calculus of variations, and in particular, since we have already established the theoretical background, we will go to a practical implementation of the methodology of calculus of variations. Basically, the practical problem which I would like to present to you right now is the one which may be one of the fundamental problems from which the calculus of variations as a theory actually started. So it was the end of 17th century when one of the famous mathematician and physicist, whatever, Johann Bernoulli, came up with a very interesting problem. The problem is as follows. If you have 2 points above the ground, so there is a gravitational field acting, and we assume that the gravitational field is uniform. And you have some kind of a track here and a ball which frictionlessly going with a zero initial speed down from point A to point B. Now, what would be the trajectory of the fastest descent? So how should we construct this track in such a way that the ball will come from A to B in the shortest period of time? Well, I mean, probably the first thing people think about is a straight line. Well, it's possible. But at the same time, if you go with this kind of a shape, the ball in the beginning will speed up faster. So maybe the overall time, although the length of the trajectory is slightly greater than straight line, but the time might be actually shorter because the speed would be higher. So anyway, he actually presented this problem to all his friends, and his friends were basically all the mathematicians who existed at the time. And it was a very interesting actually problem, and there were not one but a few different solutions, and one of the solutions actually was presented by Euler, which was a Swiss mathematician who at the time was working in Russia, and there was Lagrange a little bit later in France, and basically all these combined efforts came to calculus of variations as we know it. So basically all this story I was talking about in the previous lectures, and one of the things which was presented was Euler-Lagrange equation, and here is I will just repeat it basically. So if you will describe this trajectory as a function, so this is A, this is B, this is A, and this is capital B. So the function f of x is defined on interval from lowercase a to b, and it basically has to be equal to capital A at point lowercase a and capital B at point lower b, and we have to find this function in such a way that the time, and the time was actually a function of the function, which is called functional, that this would be the shortest. And this particular trajectory, this curve, was called Brachistochrone, and I think that pronouncing this word is probably the most challenging part of this lecture for me. Anyway, it actually comes from Greek. Brachistos is something like the short or the shortest, and chron, everybody knows what chronus is, that's time, so it's the shortest time, basically. Okay, so the question is, what is the equation of Brachistochrone which connects points A and B? And Euler and Lagrange both actually came up with a differential equation for a particular kind of functionals. If this function is described as something like integral of x, f of x, and f prime of x dx. So f of x is function, this is derivative, x is obviously argument. So if our functional looks like this, and there are some other functionals, but if it looks like this, then the particular function f of x, lowercase f of x, which makes the whole functional minimum or maximum, well, depending on certain other conditions, is supposed to satisfy the differential equation, which is called Euler-Lagrange equation, which do I have it here written? Yes. It's d put df of f x f prime should be equal to d put dx partial put df prime of f. The same argument, x, f, and f prime. So this is partial derivative by second argument. This is partial derivative by the third argument, the derivative of f. And this is just derivative by x of whatever comes out of this partial derivative. So this is Euler-Lagrange differential equation. I basically derived it in the previous lecture, and today I'm going to actually apply this equation to solve the Bernoulli's problem to find Brachistochrone. Okay, so let's start doing this. We need to minimize the time. All right, fine. So let's just take point x and x plus dx. This is a small piece of that trajectory. What is the time for the rolling ball to cover this particular distance? Let's call it ds. Well, we know that ds square is equal to dx square plus dy square, right? It's a Pythagorean theorem. So that's the length. Now we need the speed. To find out the time, we need the speed. So what is the speed at point x? Well, that's where we can come up with the solution using the energy conservation law. Now, whenever our ball is at the initial position, there is no kinetic energy, only potential energy, and potential energy is mg and the height above the certain zero level. Let's call it, so that's A. Now, at this particular level, potential energy is less. It's mg. This is function f of x, right? So it's f of x. But there is also a kinetic energy. And kinetic energy, it depends on the speed. That's mv of x squared divided by 2. And these are supposed to be equal. The kinetic energy at this point is equal to 0, but potential is this one. At this point, potential is less, because the height is less, but there is a kinetic energy, from which we can derive the formula for v, for the speed. And if we will divide ds by v, that would be the increment of the time on this particular thing. What happens then? Then we will integrate from a to b this dt, and that would be the total time. So that's the plan. As soon as we will get total time, that's a function actually of the trajectory, function of function, that will be our functional. And if this particular thing would look like this, like this, which it will obviously, then we will use the Euler-Lagrange equation, and then we'll try to solve it. So that's the plan, right? Okay, so we will implement it. That's very easy. So ds is square root of this. Now, what is dy squared? Dy squared is df square of x, right? That's what dy is. So we have function f, we have x, and as far as this is concerned, we will put it, again, we will solve it for v. M obviously goes out. So as a result, let me just write down the result of this arithmetic. That's simple. So I will just write the result basically. So dt, which is basically ds divided by v, that would be square root of 1 plus f of x square divided by square root of 2g a minus f of x. So this is the formula, and again it's very easy because ds actually, I have already determined this in the previous lecture, that this is square root of 1 plus f prime. So if we will integrate it from a to b, that is our functional of f of x. This one, which we have to minimize. We have to find such f, let's say f0, which minimizes this functional, which means it's supposed to satisfy this particular equation. So f function is this. You see, this is the function which basically gives us x, f, and f prime. Actually, there is no explicit dependency on x, just on f and f prime, from f and derivative of f, which actually is easier. Another thing is we can drop to g because it's just a multiplier. If we have to minimize this, it's the same as if we will minimize it without fg to g. So that's kind of easy. All right. So if I will construct this Euler-Lagrange equation based on this particular function. So the function f of x, f, and f prime is what? Square root of 1 plus f prime of x square divided by a minus f of x. So this is our function. So we can do is we can just do the partial derivative by f, partial derivative by f prime, then total derivative by x, and we will get a differential equation, which I'm going to write right now. I don't want to exercise my skills in deriving this derivative, and everything actually is described quite in details in notes for this particular lecture. Notes on Unizor.com. Okay, so I will tell exactly how to reach it. Basically, you will see it. If you will watch this lecture from the Unizor.com, then you will see the video presentation, and on the side you will have all the notes where I derive the equation in more details actually. I just want to save some time right now because this is just technicality. to take the derivative is not really interesting actually. You just do it basically. Okay. So again, if I will do all these partial derivatives, I will get the following equation, which I will write in a ready-to-use form. So if this is my equation which describes Brachistochrone, the shortest by time trajectory of descent, then this function y is supposed to satisfy the following equation. After all the simplification, actually, it's much simpler than you think. So y is this f0 of x. The solution, basically, of this is the trajectory. So y is f0 of x. So this is derivative by x, and this is second derivative by x. So whenever you will have a derivative, partial derivatives and total derivative of that formula with the square roots, etc., you will get this one. And again, the details you can have in the notes. Details are technicalities and not very interesting. What is interesting is how to solve this particular differential equation. And well, you have to actually get lucky, quite frankly, because there is an approach which is not really obvious, but, well, it works, and it's quite interesting actually how it works. If you will look very carefully on this, you can divide this thing into two different parts. One part and the second part. Now, what is a derivative of 1 plus y squared d per dx? Well, this is constant, 1, so it's 0, and derivative of y prime is square, would be 2 y prime y second derivative. Now, if you compare it with this, there is missing argument here. Alright, so what if we will multiply the whole thing by y prime? So you will see y prime, 1 minus y prime square, minus 2 y prime y double prime, a minus 1 y a. It's still equal to 0 because you're just multiplying by a derivative. But why is it better? Well, here is why. Y prime, well, minus y prime, is a derivative of a minus y. You see, a minus y, and this is almost derivative of a minus y. So I will put minus here, a here. Now, if I put minus here, I have to put minus here, right? I mean plus here. So everything is multiplied not by y prime, but by minus y prime. It will be this one. And I have replaced minus y prime with a minus y prime, because again, a is a constant, so derivative of a minus y prime is the same as minus derivative of y. So that's why I divided this. And this, I can, instead of this, put y prime prime. Almost like this. But nothing is wrong with putting here, right? And what do we hear? A minus y prime times something, then something prime times a minus 1. What is it? Well, this is a derivative of their product, remember? Product of two functions, u, v, derivative is u derivative v plus u, v derivative. That's exactly what we have. This is u, this is v. This is u prime v, and this is v prime u. So this is basically a derivative of a minus y times 1 plus y squared derivative of everything is equal to 0. Why is it better? Because this is second derivative, and there is no second derivative here, only the first derivative, because I can write now, instead of prime equal to 0 when the prime is equal to 0, when this is equal to some constant. I don't know what is the constant, but we have some initial conditions which will help me to do it. And now I have an equation of the first order. Okay, is it better? It is better, and here is why. Now let's talk about this particular equation. This one we can solve actually. Now, how can we solve this equation? Well, actually very simply, because what we do is we just solve it for y prime. Y prime is equal to y prime square is equal to c minus a plus y divided by a minus I. Right? C divided by a by this minus 1 will give you this. Right? Let me start again. C divided by this minus 1. So you go to the common denominator. So that would be minus a plus y. Okay, so y prime is equal to square root of this, but I have to be careful. I have to put plus minus, right? Okay. Now, why is it better? Very simple. Well, first of all, let me just take that this is supposed to be only minus. Why? Because the function is diminishing, which means its derivative is supposed to be negative. Now this is a square root of something, this is a positive thing, so that's why we put minus here. Now this is dy by dx, right? So what follows from here? We can separate y and x. We will put this into the denominator, so I will flip it. So I will have dy divided by, well, not divided now, I will multiply it by inverted. So it will be square root of a minus y divided by c minus a plus y. Dy is equal to minus dx. And dx will be here, right? Why is it better? Very simply, because I can separate these things and integrate separately. I can take this integral, well, this is easy, this is minus x plus some constant, e. And this is also, it can be done manually. I'll just write again, I will write the result of this, because I don't want to waste time on details in this particular case. That's c arc tangent of square root c minus a plus y divided by a minus y plus square root of a minus y minus c minus a plus y. And this is equal to, well, plus some constant, since it's an indefinite integral. So this is basically, if you will check, if you want to check, you can just take this derivative of this and you will get this. And the integral of minus x would be minus x plus another constant. But we can combine these two constants, d and e, into one constant, and that would be the result. So c and d are some constants. C and d are some constants which are not defined, because with any value of these constants we will have a solution of differential equation. But we do have two different conditions. Function of lowercase a equals capital A, and function of lowercase b is equal to capital B. So we can put a and b, lowercase a and b, getting uppercase a and b, and that would be two equations with two different c and d unknowns, and we can solve it, and we will get c and d. Well, to tell you the truth, equations are transcendent, so arctan and this square root, it's not really well expressed in real formulas. But I mean, it's still equations, and you can solve them numerically or any other way, which I did for one particular case. And I will tell you what. So basically, this is a solution. Now, it's a little bit non-typical. It's not like y is equal to function of x. It's x is equal to function of y. Does it make a difference? No, because you know that the graph can be basically constructed anyway, and which I did with Desmos. There is a package on the web. So if you will actually try to set 5, 1, 1, 4. That's what I decided. So 1 and 5 is the beginning, 4 and 1 is the end. So I have capital A, I have A, lowercase a, b, and capital B. So if I substitute x and y, correspondingly lowercase and uppercase a, I will get one equation. If I will substitute for x and y lowercase b and capital B, I will get another equation. I numerically solved them. I just graphically, to tell you the truth, to make my life easier. And I got basically the values. I got c is equal to what? 5.8, d is equal to minus 10.1, and if I basically graphed it, I will get exactly the curve like this, connecting these points 1, 5 and 4, 1, and that was my Brachistochrone. So that's basically it. I deliberately didn't want to go to all the tedious details of having derivatives and all that. It's all technical stuff which everybody who knows calculus can do by himself. I just wanted to concentrate on something which is really essential for this particular problem. And essential was constructing the equation from the physical perspective, and basically solving this equation, which had this little trick which I was explaining. By the way, from the physical perspective, if you have the ball going down along this trajectory, what kind of forces are actually acting in this particular case? Why is it moving along this curve? Well, obviously, if this is your ball, there is a weight, which is gravitation, which is mg, and there is a reaction of the track. Let's call it r. So this is p, this is r, and the resulting sum of these two vectors is supposed to give you the vector which is tangential at any point, is tangential to this curve. And that's the result of the sum of these two vectors is the vector of force, which actually forces the ball to go along this particular curve. Now, this force is always the same, but this force reaction of the track is obviously different, and the result is that the body, the ball, whatever object, is moving along this particular curve, regardless of the curve, by the way. So no matter what curve is, the reaction would be perpendicular to a tangential. So here you go. Now, another thing which I wanted to mention was, this is some kind of an analytical formula style solution. Usually when people are talking about Brachistochrone in textbooks, they do not derive this particular formula. Sometimes they do, but very rarely. Usually, instead, they are doing something like parameterize two functions depending on some angle, and angle is usually the angle from the vertical. Now, then it will be a little bit more obvious how this particular curve looks like. It's actually a cycloid. What's a cycloid? Cycloid is this one. If you have a disk, let's say, and there is a point, and you will roll the disk along this. Cycloid would be something like this. Now this is a reverse cycloid, so the disk would be rolling from beneath actually. Then you will have something like this. So this is basically a piece of cycloid. And in parameterized way, if you will solve this differential equation using parameterized way, that's kind of more obvious that this is cycloid. But I didn't really go this way because it's not really the purpose of this lecture. The purpose of this lecture is Euler-Lagrange differential equation applied to some practical problem. Okay, that's it. Now, I do encourage you to watch this lecture from Unizor.com. Even if you found it somewhere on YouTube or wherever, it's still better because you will have the lecture itself and the notes for it, and the notes contain much more details, including the derivation of the integral, derivatives, etc. So, plus Unizor.com contains other courses. Well, there is obviously a prerequisite for this course, which is Math for Teens. This is Math Plus and Physics Plus. There is a Math for Teens and there is a Physics for Teens. So they are prerequisite, and also it's not just a lecture by itself. That's the part of the course. So you have all the prerequisites, you have all the lectures which precede this, etc. And that's why I recommend you to go to Unizor.com. In this case, course is Physics Plus, and you will choose variations, and that's where you find all these lectures about variations, including this one about Brachistochrone. Okay, that's it for today. Thank you very much, and good luck.